Feature selection represents a crucial step in the data processing pipeline within data science. It is a methodical approach designed to identify and retain only the most relevant features, or variables, from a data set. Concurrently, this process systematically discards features deemed irrelevant or redundant for the analytical task at hand. The impact of effective feature selection is profound, significantly influencing the performance of predictive models. It directly contributes to improving model interpretability, making complex models easier to understand and explain. Furthermore, it substantially enhances computational efficiency by reducing the processing load. This technique is instrumental in reducing the dimensionality of datasets, which is particularly beneficial for high-dimensional data. Ultimately, feature selection helps data scientists build more robust, accurate, and generalizable models. Its application is fundamental to achieving optimal outcomes in machine learning projects. One of the primary goals of feature selection is to improve model accuracy. By focusing exclusively on the most informative variables, models can better discern underlying patterns. This process effectively mitigates the noise and bias that can be introduced by irrelevant or weakly correlated features. Crucially, feature selection plays a vital role in preventing overfitting, a common challenge where models perform well on training data but poorly on unseen data. By simplifying the input space, it improves the model's generalization performance, ensuring reliability across diverse datasets. This leads to more dependable predictions in real-world scenarios. Beyond accuracy, feature selection offers significant advantages in model simplification and efficiency. Reducing the number of features inherently makes models less complex and easier to comprehend. This simplification is invaluable for communicating model insights to non-technical stakeholders. A reduced feature set directly translates to faster training times for machine learning algorithms. This efficiency is critical when working with large datasets or when rapid model iteration is required. Moreover, it enables faster prediction times, making models more practical for real-time applications and deployment. Feature selection techniques are broadly categorized into three main types: filter methods, wrapper methods, and embedded methods. Each category employs distinct strategies to evaluate and select features, offering different trade-offs in terms of computational cost and performance. Understanding these distinctions is key to choosing the appropriate technique for a given problem. Filter methods assess the relevance of features independently of any specific machine learning model. They rely on statistical measures to quantify the relationship between each feature and the target variable. Common statistical measures include correlation coefficients, mutual information, and chi-squared tests. Features are then ranked based on their calculated scores, and a predetermined number of top-ranked features are selected. These methods are highly advantageous due to their computational efficiency and speed, making them suitable for large datasets. They can quickly prune a vast number of irrelevant features before model training begins. However, filter methods have limitations. They do not consider interactions between features, meaning they might overlook complex relationships that only become apparent when features are combined. This independence from the model can sometimes lead to suboptimal feature subsets for specific algorithms. Wrapper methods evaluate subsets of features by training and testing a specific machine learning model. The performance of the model, typically measured by metrics such as accuracy or F1 score, serves as the criterion for feature subset selection. This iterative process directly optimizes the feature set for the chosen model. Examples of wrapper methods include forward selection, where features are incrementally added, and backward elimination, where features are progressively removed. Recursive feature elimination, or RFE, is another prominent wrapper technique that repeatedly builds a model and removes the weakest features. These methods inherently consider feature interactions and the specific needs of the model. The primary advantage of wrapper methods is their generally higher accuracy compared to filter methods, as they are tailored to the predictive model. They often yield feature subsets that result in superior model performance. However, their main limitation is their computational expense, especially for large datasets with many features, due to the repeated training and evaluation of the model. Embedded methods integrate the feature selection process directly within the model training algorithm itself. These techniques automatically assign weights or coefficients to features during the model building phase. Features with lower weights or coefficients are effectively deemed less important and can be discarded. Prominent examples include L1 regularization, also known as lasso regression, which drives the coefficients of less important features to zero. Tree-based models, such as random forest and gradient boosting, also inherently perform feature selection by evaluating feature importance during their construction. These models can provide a ranking of features based on their contribution to predictive power. Embedded methods offer a compelling balance between accuracy and computational efficiency. They are generally less computationally intensive than wrapper methods while still considering feature interactions. This makes them a practical choice for many real-world data science applications, providing good performance with reasonable training times. The choice of feature selection technique is not universal. It depends on several critical factors. These include the specific characteristics of the dataset, such as its size and dimensionality, and the nature of the features themselves. The particular machine learning model intended for use also heavily influences this decision. Furthermore, the overarching goals of the analysis, whether prioritizing interpretability, predictive accuracy, or computational speed, must guide the selection process. Often, a combination of techniques or an iterative approach involving different methods yields the best results. Experimentation and cross-validation are essential for validating the chosen feature set. Ultimately, feature selection is a crucial practice for building effective and insightful data science models. It is not merely an optimization step but a fundamental aspect of data preparation that directly impacts model quality. By carefully selecting relevant features, data scientists can unlock the full potential of their data. This meticulous process enables the derivation of more meaningful insights, leading to more robust predictions and better decision-making. Mastering feature selection is therefore indispensable for any aspiring or practicing data scientist.